Hello everyone, today our group will present about binary system of copper-silver alloy. Our group members consist of me, Georgian, Zeti, and Sade. This is the agenda for today's presentation. Okay, so first of all, what is binary alloy system? A binary alloy system consists of two components, either elements or compounds that can form a mixture, either solid or liquid. One such important system is copper-silver alloy. This alloy is well known for its exceptional electrical and thermal conductivity, combined with mechanical strength and corrosion resistance, making it ideal for numerous engineering applications. In this presentation, I'll break down its application, why it's chosen, and the components that define it. Let's start with the key engineering applications of copper-silver alloys. First, electrical conductivity. This alloy is widely used in high-performance electrical wiring and switch contacts because of its superior conductivity. Second, its durability. The addition of silver improves copper strength, which is why it is commonly used in coin, jewelries, and metals for their durability and aesthetic appeal. Third, thermal conductivity. It is also ideal for applications like heat exchanger and thermocouples where high thermal performance is critical. Fourth, it is corrosion resistance. Copper silver alloys are resistant to oxidation and corrosion, making them suitable for outdoors or marine applications. And lastly, wear resistant, which makes them suitable for bearings and bushings in high stress environment. Okay, next, here's the reason why we choose copper silver alloy. First, copper silver alloy offers a unique combination of properties. Just like I said on the previous slide, it offers high electrical and thermal conductivity along with improved strength and corrosion resistance. This balance makes it suitable for a wide range of applications. For example, in electrical wiring, the alloy retains excellent conductivity while being stronger than pure copper, which is crucial for durability in high-performance environments. Second, it is versatile, serving industries ranging from electronic and decorative applications. It can be processed through casting, forging, and rolling, making it cost-effective for mass production. Additionally, its properties can be tailored by adjusting the copper to silver ratio depending on the specific requirements of an application. Next, it also has eutectic composition that enables uniform solidification, resulting in fine-grained microstructure that enhance the alloy's mechanical properties. And lastly, adding silver to copper also brings unique mechanical advantage, such as it increases the tensile strength, which is important for applications like overhead power lines, and also it is important to improve hardness, which is help components to resist wear and deformation in environments with high mechanical stress, such as bearings and bushings. Okay, so now let's take a closer look at the components of the copper-silver alloys. The primary elements of the copper-silver alloy are copper, Cu, and silver, Ag. Copper contributes high conductivity and ductility, while silver enhances strength, wear resistance, and corrosion protection. In terms of phase behavior, we have alpha phase, which is a copper-rich solid solution containing a minor silver, and beta phase, which is a silver-rich solid solution with minor copper. The system also has a eutectic composition, which occurs at approximately 28.1% weight of copper and 71.9% silver. At the eutectic temperature of 779 degrees Celsius, the alloy solidifies into a uniform mixture of alpha and beta phases. Also, this phase behavior is what gives the alloy its unique properties and makes it suitable for diverse applications.
Next, I will talk about the type of phases. This system has three main categories: the liquid phase, solid phase, and the eutectic phase. First, we have the liquid phase. This phase exists when silver and copper are heated to high temperature above the liquidus line. In this step, the metals form a homogeneous solution. The liquid phase occurs when the temperature is above the melting points of both elements or when mixture are heated beyond the eutectic temperature. Next, the solid phases, which consist of two key types, the alpha phase and the beta phase. The alpha phase is a silver-rich solid solution that contains a limited amount of copper dissolved in it. This phase forms when the alloy composition is predominantly silver and is cooled below the solidus line. It has a phase center cubic FCC structure, which gives it excellent electrical and thermal conductivity. On the other hand, the beta phase is copper-rich with a small of silver dissolved in it. It forms when the alloy is copper dominant and cooled below the solidus line. Like the alpha phase, it also has an FCC structure but it possesses different mechanical properties, making it stronger and harder than the alpha phase. Finally, we have the eutectic mixture, which is a combination of both alpha and beta phase. This microstructure is formed at the eutectic composition of 28.1 weight% copper at a temperature of 779 degrees. The eutectic mixture consists of alternating layers of the alpha and beta phases, offering a balance between ductility and strength. This makes it particularly useful in applications such as soldering and brazing alloy. Next, I will talk about the phase field in the silver-copper phase diagram. This diagram helps us understand how different phases form depending on the temperature and composition. Let's start with the single phase field. These regions contain only one phase of the alloy. The liquid field exists above the liquid line when the entire alloy is in a molten state. The solid alpha field represents a silver-rich solid solution that exists below the solver's line. The solid beta field is a copper-rich solid solution found below the solver's line. Now, let's move on to the two-phase field, where two different phases coexist. In the liquid plus alpha field, we have both liquid and solid alpha phase coexisting during partial solidification. The liquid plus beta field contains liquid and solid beta phase together. In the liquid plus alpha plus beta field, which occurs when in the eutectic composition range, liquid coexists with the eutectic solid mixture of alpha and beta phases. Finally, the alpha plus beta phases field is a solid solution mixture of both alpha and beta phases, which is found below the eutectic temperature. Influence of temperature on composition. Temperature has a significant impact on the composition and phase transformation within the silver-copper system. At high temperature, above 779 degrees, the alloy exists in a liquid state. In this state, the solubility of copper in silver increases with temperature, and the same happens with the silver in copper. If alloy composition is outside the eutectic range, solidification occurs gradually, starting with the formation of either the alpha phase or beta phase depending on the composition. At exactly 779 degrees, a special transformation known as the eutectic reaction takes place. The liquid alloy transforms directly into a fine mixture of alpha and beta solid phase. This eutectic structure provides a good balance of mechanical strength and thermal properties, making it useful in applications like soldering. Once the temperature drops below 779 degrees, the structure of the alloy depends on its composition. The material may consist either the alpha phase, the beta phase, or a combination of both. During slow cooling, phase transformations such as precipitation or phase segregation can occur, which may affect the alloy mechanical properties. Influence of temperature on pressure. While this system is mainly affected by temperature, pressure can have some minor effect, especially in extreme environments like deep sea or aerospace application. First, pressure can slightly impact the solubility of copper in silver. Higher pressure may shift phase boundaries by altering solubility limits. However, in most particle situations, this effect is so small that it can be considered negligible. Next, pressure can influence the melting point of the metals in the system. Increased pressure generally raises the melting point, meaning the eutectic temperature may shift slightly under high pressure condition. Lastly, extreme pressure condition can lead to change in the alloy microstructure. Phase stability may be affected, potentially leading to the formation of metastable phases with different properties compared to those formed under normal conditions.
Thank you to the previous presenter. My name is Sade and I am going to touch on the lever rule analysis for the phase diagram of copper-silver alloy. First and foremost, what is the lever rule? Lever rule is a mathematical tool to quantify the phase composition in the binary system, which in this case is copper and silver. Lever rule applies the principle of mass conservation in order to calculate the mass fraction of each phase composition at chosen temperature and pressure. Performing lever rule calculations consists of 3 steps that are shown in the slide. First, draw a horizontal tie line across the 2 phase region at the chosen temperature of the alloy. Second, mark the overall composition alloy on the tie line. The value for the overall composition is arbitrary. Lastly, the mass fraction of one phase is calculated by taking the length of tie line from the overall alloy composition to the phase boundary of other phase, dividing by the total tie line length. These steps will be implemented when we want to find the mass fraction for the phase composition for the copper-silver alloy. Before we proceed with the calculation, I am going to explain the derivation of lever rule to obtain the lever rule formula. As I have mentioned before, lever rule applies the principle of mass conservation, which will give us the equation of mass fraction of alpha plus mass fraction of beta equal to 1, which I denote as equation 1. Conservation of the component also gives the second equation, which is mass fraction of alpha multiplied by composition of alpha plus mass fraction of beta multiplied by composition of beta equal to overall alloy composition. From equation 1, we arrange it to isolate mass fraction of beta on the left-hand side by subtracting mass fraction of alpha on both sides. Thus, it will be the new equation 1. Substitute equation 1 into equation 2, then solve it by algebraic method to obtain the formula of mass fraction of alpha, which is overall composition subtracted by composition of beta is divided by composition of alpha subtracted by composition of beta. To find the formula of mass fraction of beta, we arrange equation 1 so that the mass fraction of alpha is on the left-hand side. Hence, that is how to obtain the lever rule formula from
Now I am
derivation.
going to perform calculations on the copper-silver phase diagram. For the calculation, lever rule is applied at 35 weight% silver and 65 weight% copper at temperature 779 degrees Celsius. Before substituting any value in the formula, perform the steps that have been discussed in the slide before in the phase diagram. By doing this, we can identify the type of phases and its composition. At 35 weight% of silver, it is an alpha plus beta region, where both alpha and beta coexist. The composition of both phases can be directly read off, which are 8.0% of alpha composition and 91.2% of beta composition. Once all the value is obtained, substitute it into the formula that has been derived earlier to find the relative mass fraction of each phase. As you can see in the slide, the mass fraction of alpha is 67.5%, while the mass fraction of beta is 32.5%. That is how to obtain the mass fraction of alpha and beta at 35 weight% of silver at temperature 779 degrees. Now I am going to cover the interpretation of the result, practical implications, and finally error analysis. First, the lever rule helps to identify the right composition to achieve desired material properties. In the analysis, the alloy consists of 67.5% of alpha phase, which is copper rich, and 32.5% of beta phase, which is silver rich. The dominant of alpha phase shows that the alloy primarily composed of copper atoms as the main crystalline structure, with the beta phase as the secondary silver rich structure. The result aligns with the phase diagram that falls within the alpha plus beta phase. Both phases coexist in equilibrium. Now, let's discuss the practical implications. The weight fractions indicate how much alpha and beta phases are present. This helps engineers to predict alloys' properties. A high percentage of alpha phase suggests that the alloy exhibits properties like copper, such as being malleable and having high electrical conductivity. Meanwhile, the presence of beta phase increases the alloy's hardness and strength, which enhances its durability compared to pure copper. Adding silver to copper alloys improve the mechanical properties, but also reduces its electrical conductivity. Thus, with the help of lever rule, engineers can design a balanced copper-silver alloy that has efficient electrical performance with mechanical improvement. Lastly, let's look at the error analysis. The lever rule assumes idle phase behavior at a given temperature and that both silver and copper are pure. However, in real-world conditions, equilibrium might not be achieved due to kinetic limitations. Additionally, any impurities in the component could alter the phase fraction and properties. Misinterpreting the tie lines or phase boundaries on the phase diagram can also induce errors. Lastly, temperature variations can shift the phase compositions, altering the mass fraction of alpha and beta phases. To summarize, the lever rule is an essential method to determine the phase fraction, which help to predict and tailor material properties. However, real-world limitations and potential error must be accounted for when designing alloy like the copper-silver system.